So welcome back to this MIMO channel. So everything so far was narrowband MIMO, right? So there is no delay spread in the channel so far. What happens when we have wideband MIMO? So this is this one. I only spent one slide on this. In this case, you would use something called MIMO OFDM. How this works is as follows. So we again have our transmit array where we send signals over each of the antennas. We have our received array where we receive the signals. And then we have our channels. And now each of these channels will have some delay will have some impulse response. So as a function of tau, there will be some taps in the channel. So it's not a narrowband channel anymore. That these H's are just complex numbers. Now it's a vector of complex numbers. Now to deal with this, what is typically done is something called MIMO OFDM, where at each transmit antenna you have an OFDM transmitter. So here. These are all perfectly synchronized. Then over each transmitter, we send our data symbols. So these are then in the frequency domain. We apply our IFFT, we do then the cyclic prefix insertion, and then we have a synchronized OFDM transmission here. At the receiver, we do our standard processing, but synchronized between the different receive antennas. So this means we filter, sample, remove the cyclic prefix, and then go back to the frequency domain. And then it turns out, if you look at a certain subcarrier here, you will have some observation. Let's call this ZK. And if I work in discrete time, then here I would send XK. So this would be a vector of, oh, sorry. That's not correct what I'm saying. If we look at a certain subcarrier, the kth subcarrier, then across all of the transmit antennas, we send data symbols xk of size mt by 1. And at the receiver for one subcarrier k, we'll have an observation zk, which is r by 1. And then the relation between this xk and zk is given by this expression. Okay, so you have per subcarrier an observation, which depends on what is transmitted on that subcarrier, times the channel plus noise over that subcarrier. And you have this for k equal from 0, or let's just say from 1, till the number of subcarriers. So you create in MIMO FDM and sub little MIMO systems, and each of these has now a flat channel. Flat or narrowband channel. So this means whatever we learn for narrowband MIMO, we can easily extend to the wideband MIMO case. So as I said, the idea of MIMO breaks down into two parts. One is when the channel state information is only available at the receiver, and then later we will see what happens when the channel state information is also available at the transmitter. So now the problem that we have is of the following form. We receive Y. We know what is the channel because we have channel state information at the receiver. We know the noise statistics and we want to recover X. How you solve this problem is, well, it's a standard detection problem, right? We've seen problems of the form Y is HX plus N before for scalar cases. This is for the SISO channel. We've also seen observation models of this form. Y is H transpose X plus N for the diversity systems. Okay, that's misspelled. And for all of these, we know how to apply maximum likelihood. So now it becomes relatively straightforward to also do it here for the MIMO system. Okay, by definition, the maximum likelihood estimate of X is you solve the following optimization problem. You find the X that maximizes the likelihood. Okay, and this is a Gaussian likelihood now, of course, because the only thing that's random is the noise, and the noise is Gaussian. And then following the standard steps that we did before, this means that you take the logarithm and then you remove all the constants that are not necessary. You find that you will solve a minimum Euclidean distance detection. So that means that for given Y, so Y is frozen, you've observed Y. H is also given. You plug in each possible X, and then you evaluate this cost function. Okay, so this I can write here equivalently as arg min over all possible x's, some cost function of x. And now the problem is that the complexity of this approach is quite high. So let's suppose that we have BPSK and we have two transmit antennas. So this means that MT is equal to 2. Okay, then we will evaluate C of -1, +1. Well, no, let's start from the beginning. -1, -1, -1, +1, +1, -1, and C of +1, +1. Okay, and these are 4 numbers, and I will just pick whichever gives the smallest cost, and then I will say, this is my decision. Okay, now, if MT is equal to 3, then I will have 8 combinations instead of 4. And now if I use, for instance, QPSK and MT is equal to 2, how many combinations do I have then? It will be 4 to the power 2. And in general, if you have M-point constellation, the number of x's, so the number of times you need to evaluate this cost function, will be m, the size of the constellation, to the power of the number of transmit antennas. And this is a number that grows very, very quickly. So this means that typically maximum likelihood will have very high complexity. There are other detectors, so you can think, well, if you have this observation model, maybe the first thing you would think about is why not just invert the channel. And this is called the zero forcing detector. So when the number of transmit and receive antennas is the same, then you can just say, okay, I create an observation Z, which is H inverse times Y, which will give me H inverse HX plus H inverse times the noise, right? Which will give me X plus H inverse times the noise. That's fine, but this doesn't work when MT is different from MR, right? Because then the inverse does not exist. But there exists a generalization of the inverse. This is this thing, and this is called the pseudo-inverse. And you can apply this when the number of receive antennas is more than the number of transmit antennas. You can already intuit that when you have more transmit antennas than receive antennas, you cannot apply in any kind of inversion, right? If you send with 10 transmit antennas, 10 QAM symbols, and then you have only one receive antenna, you have no hope to recover your data. But when you have more receive than transmit antennas, you can apply this technique. Okay, so this is called the pseudo-inverse. When you now plug in what is H and you work it out, you will get this expression. So this looks really great because now we can immediately recover X, right? So in a sense that from Z1 is X1 plus W1, and then we say we can find X1 hat. From Z2 is X2 plus W2, and we find X2 hat. And now the complexity is again independent of the number of antennas. Well, it's actually linear with the number of antennas and linear in the size of the constellation. So this is very good. The problem now is with this noise. It is possible that when the matrix is not well conditioned, that this inverse is very, very large, right? And we'll see an example of this soon. And then this noise will be extremely large, and this is called noise enhancement. So this tends to work very poorly when the channel is not well conditioned. So when this inverse has, okay, when H Hermitian H has is not really full rank, then this inverse will explode and then your noise will explode. There is a third detector called the MMSE detector, which applies a variation of this pseudo-inverse. So you have here an additional term which depends on the signal-to-noise ratio. And again, you have an observation model that is now approximately X plus W. And then again, you will say Z1 is approximately X1 plus W1. And then you find an estimate of X1. This means that the complexity of the detector is again mt times m, so that's good, still this linear complexity. And you will typically have better performance than zero forcing. And you can derive this detector from the MMSE criterion, where you assume that X is Gaussian, and then after some math, you will find this expression. Okay, so some notes here. We've seen that zero forcing MMSE requires a simple decision step based on Z. Okay, because now each element in Z is directly each element in X plus noise, so we can recover the individual elements of X from the individual elements of Z. So we have linear complexity. Of course, we need to compute these inverses, and this has some complexity as well. Yeah, and then also, as I mentioned, the MMSE detector relies on a Gaussian model for X. So let's do an example. Suppose now you have a system with MT is MR is equal to 2, and now your channel looks like this. So this means the channel matrix is 1, 2, 1, 2 plus epsilon. And you see already when epsilon is 0, this channel is not invertible. We use BPSK. We have a high SNR of 50, so 17 dB. And I want you to solve the following problems. And you can do this in MATLAB if you want. So compute the inverse of the channel, compute the maximum likelihood detector, zero forcing detector, and MMSE detector. See something about the complexity and about its potential performance. So I recommend you spend a few minutes, pause the video, and then come back when you've solved it. So welcome back. So okay, this was our problem. We had this channel here, and we were looking at the inverse of the channel. So the channel inverse looks like this. And you will see here that when epsilon is very, very small, these entries in this inverse of the channel will be large. And this will have some implications for the zero forcing detector. For the maximum likelihood detector, what we will do is for each given observation y, we will compute Euclidean distance between y and hx. So how does this work? We remember that we have BPSK, so we can represent the transmitted symbols on the first antenna and the second antenna in a kind of constellation plot. Okay, so these are all the points that we could send out. So this point is given by square root of rho 1, 1. This point is given by square root of rho 1 minus 1. And so forth. So these are the possible x's, and then what happens after the transmission over the channel, we have hx, right, which is h x1, x2. Then we have in our observation domain, so I call this y1, y2. So let's first look at the noise-free observations. Where could those end up? And now I don't know exactly, I haven't tried this, but let's say that they will end up something like this. Okay, so this means that this point here, after passing through the channel, will end up, let's say here, and this point here will end up, okay, I don't know, maybe here. I'm just making a guess. You can evaluate this yourself by just multiplying the transmitted points with the constellation, with the channel matrix. And where they will end up depends, of course, on epsilon. And you will see that when epsilon tends to 0, then these points will collapse. So some of these points, they will be on top of each other. And now our observation lives somewhere in this space here. So then we receive some kind of observation, let's say here, right, which will be, let's say, this transmitted point. And then because of noise, it will end up here. And then to make a decision, what we do is we compute the distance between the received point and each of the mapped transmitted points. And the one that is closest, we say, okay, then this was the decision. And we expect the performance of this to be quite good, provided these points in this decision space are well separated. So the mapped constellation points should be well separated, and then the maximum likelihood will be good. Complexity is low because we only have 2 transmit antennas and 2 points in the constellation. So it's 2 to the power 2. There's only 4 different combinations to check out. So this was the zero forcing detector. Then for the, no, sorry, the maximum likelihood detector, for the zero forcing detector, we will invert this matrix. And if we look at the specific value, I forget what was the number, 0.01, this is the inverse of the channel, right? And then what we do is we will compute Z, which is H inverse Y, which will give us X plus H inverse N. And now this noise will have very large covariance. So what we will receive after going to the Z domain, so we have Z1 and Z2. If there was no noise, we would again get perfectly our points. So square root of rho 1, 1. This is without noise. But then the noise will, let's say, our observation in the absence of noise would be some point here. But then due to the noise, this noise is kind of very, very large, but typically along one dimension. Okay, so this is the noise enhancement. And then finally, the MMSE matrix, the MMSE detector uses this, doesn't use this inverse, but uses a slightly different matrix, and it turns out to be looking like this. Okay, so it's much better conditioned, so the noise will have less power than in the zero forcing case, but it will be some residual interference, so that you don't have exactly that the first element in Z is X plus noise, but there will be some symbol interference. So this ends the part regarding channel state information at the receiver. Now we go on to the case where channel state information is at the transmitter. But we have one more slide. This picture is, I took this from this paper where they compare different detectors as a function of signal to noise ratio. And if you want to see all the details of the channel, you can look into this paper. But my point is that it shows zero forcing here. So signal to noise ratio as a function of symbol error rate, maximum likelihood at the bottom. And you see that there's a big gap between zero forcing and maximum likelihood. And that the MMSE turns out to be on top of the maximum likelihood in this case. So the MMSE is much better. And you should use it when you can instead of zero forcing. All right, so this was a bit longer than expected, but let's take a break and then come back to the case where the channel is known at the transmitter as well.